Okay, let's get started, if we could. Welcome to Lecture 6 of the planets. We're boogieing right along. We're about to enter Chapter 4 in the book. And in fact, we're about a fifth of the semester done. It's incredible to me. Today, we're going to be discussing something entirely different. The physics of the universe. What are the laws that govern the motions of the planets, the moons, the ring particles around Saturn, the asteroids and the comets as they move around planets and the sun? We're going to be discussing, really in a flash in the pan way, all of the physics that you need to know about the universe. The laws of motion, the law of gravity, and we'll be discussing some of the issues that really govern our own daily lives. An automobile and how it gains energy, how it applies a force to the road so that a car can accelerate to high speeds. In the next lecture on Thursday, we'll be discussing energy and the nature of momentum and even angular momentum that is a natural cousin of the laws of motion and gravity. Most of what we are going to discuss today, again a snapshot of physics, really was learned back in the 1600s by a fellow who's considered the greatest scientist ever, Isaac Newton. So I'll be telling you a little bit about his discoveries and even about his way of approaching life. Let me back up for a moment and tell you some announcements. There's homework due, as always, on Friday about Chapter 4. So the first thing you should do, more than ever before, is find yourself 2 or 3 hours in a quiet place and just read Chapter 4. I promise you, what you learn in Chapter 4 and in the lectures this week represent physics that you'll keep in your head for the rest of your lives. Very, very powerful physics, useful concepts beyond science, way beyond science. So read Chapter 4 for sure. The homework is all about Chapter 4, due as always Friday at 6 p.m. And just to get you warmed up, I have a lot of questions today, so please get your multicolored card out early. And are there GSIs around yet to give out extras? They may be around soon. So if you don't have your multicolored card, you will definitely need it. I have quite a few questions salt and peppered through the lecture. Let me also remind you, while we're on the subject, that there is an observing project that I've described in the last week or so, and I hope most of you have already started. If you haven't, you're behind, because there's only 3 weeks to make your measurements of Mars, and during the 3 weeks, you are going to try to detect the motion of Mars. And so it's very valuable that you have an early observation of Mars with which to compare the position of Mars during the upcoming 2 weeks. So this is here as a reminder to look for the 3 dots of light, Antares, Mars, and Saturn. I've been watching them myself every night. Last night they were obvious. The night before they were obvious. You need a clear view, as many of you know, of the west and just south of west, and then you should be able to see the 3 dots of light. So it's a little challenging and it takes a little bit of care. And by the way, a little hint, during the upcoming 2 weeks, these 3 dots of light are going to slowly appear lower and lower in the sky. So you'll need a better and better vantage point as the next 2 or 3 weeks go by. You'll be able to see all 3 of them, but they'll be closer to the horizon. let me take a break for a moment. Any of you that don't have a multicolored piece of paper, because we have so many quiz questions today, raise your hand now so that the GSIs can hand one out to you. And I'll keep going with my lecture while the colors are flying. Let's start with the greatest scientist in history, maybe rivaled barely by Charles Darwin, and that greatest scientist ever, widely acknowledged as even more brilliant than Einstein, was Isaac Newton. You can see he lived from the 1600s through the 1700s. He studied the motions of objects in our daily lives, how a ball rolls down a hill, how an object moves along a flat surface or an inclined surface. In short, he studied the behavior and the motions of objects here on the earth. And by looking up into the sky, the night sky, he began to realize that the moon and the planets might be governed by laws of physics that were the same as the laws of physics here on the earth. This is one of the most profound moments in the history of science, realizing that the laws of science that we learn from experimentation here on the earth apply also to the realms out there in the cosmos. Newton was clearly the first person to realize that. He developed several laws of motion, and you'll have to keep your attention during today's lecture because his 3 laws of motion come at the end. We'll also discuss his law of gravity that comes earlier on. So keep an eye out for Newton's laws of motion, the 3 of them, and the law of gravity. Newton did many other things in his career. He understood that light was composed of colors, and indeed a whole range of colors, some of which were invisible to the naked eye. He also developed the first telescope that used a mirror instead of a lens. Galileo had invented the telescope that used a lens. Newton figured out a way to put a curved mirror to collect the light from the planets and the stars, the first reflecting telescope. And then, on the side, for fun, as a hobby, he invented calculus. Some of you have taken a course in calculus. Imagine what it would be like to invent calculus. So let me now tell you a little about the life of Newton, and I want to emphasize an aspect of him that I find very exciting and important for all of you. Newton had a great ability to concentrate. When he wanted to solve a problem, a puzzle, a riddle, understand something deeply, he found a very quiet place and he just concentrated on it for hours and even days straight without distractions. And I think there's a lesson there for all of us. And I want to show you a little movie about just a snapshot of his life so that you get a feeling for it. What Newton's life was like in Cambridge, England. So that's cool. You could see that there's something we can all take from his methods. I find it helps me too. If I can find a quiet place and just concentrate for a few hours, I can solve problems that I never could solve if I've got the cell phone going and texting and email. It's way better to turn off all the electronics, for me anyway, to try to get something done. And obviously people like Newton and Einstein benefited a lot from that. Now, among the types of motion that Newton studied were the positions and the speeds of objects. And so I want to first remind you of what you all know from high school about the definition of positions and speeds and velocities and heading toward acceleration. So speed is simply the distance traveled by something, like a car, over the course of some amount of time. And if you divide the distance traveled by the time it takes to travel that distance, distance divided by time is speed, sometimes called velocity. The units of speed, obviously, are the units of distance, meters or feet or miles, and time in the denominator, the units of which are seconds or hours. So in the metric system, we would say that the units of speed are meters per second. And of course, speed, as we all know from English, is simply the rate at which something moves. And you can think about many examples of speed in your daily life: the speed of a car, of a boat, of a plane, of a rocket. Speed has values like 10 meters per second or 100 kilometers per hour, the speed of a car on a highway. Now, the word velocity in science means something slightly different. Velocity means speed and direction. If you specify how many meters per second something is traveling, that's a speed. But if you also specify the direction, like up, down, left, right, east, west, and so on, a speed and a direction is a vector. And so velocity being a vector, you strictly speaking need to specify the speed and the direction to fully specify a velocity. And then you would say that distance in a certain direction is velocity times time. Why do I say that? Well, this equation here, distance equals velocity times time, is exactly the same as the equation above, where I've simply multiplied both sides of the equation by time, leaving distance alone on the right-hand side, and then speed times time on the left-hand side, and I've replaced the word speed with velocity. So, to summarize these very important equations, they are useful way beyond science, way beyond physics for sure. You can write that distance equals velocity times time. You could solve for time if you want to know how long it takes something to happen. Divide both sides of the equation by the velocity, and you have an equation for time. Very easy. So this equation can be solved for any one of the variables if you know the other two, something that you learned back in algebra in 8th or 9th grade. Of course, I have to tell you what's really on my mind. Not many of you are going to become professional physicists, but you will use this equation anyway. There are always rates of change of something. How much money is in your checking account? How many dollars you collect over the course of time might be some rate at which you collect money. And then if you know that rate, that's like a speed, and you multiply by time, that tells you the total amount of accumulated dollars. So that's like a distance. So this idea of a rate and a time over which that rate occurs comes up all the time in daily life. Now, I'd like to give you the first quiz question, and this is a hard one. Here's the quiz question, and I'm going to give you a full minute to try to work it out. Let me read it to you. An asteroid orbits the sun with an average distance, or a semi-major axis, A, of 4 AUs. And I'll remind you that an AU is the Earth-Sun distance. So this is an asteroid orbiting the sun 4 times farther away than the Earth is from the sun, 4 AUs. And the question I want to ask you, and it's not easy, how fast does that asteroid travel? What is its speed around the sun relative to, compared to, the speed with which the Earth orbits the sun? What's the speed of the asteroid? Is it faster or slower than the Earth goes around the sun, and by how much? Does the asteroid go 25% as fast as the Earth, half as fast as the Earth, twice as fast as the Earth, or 4 times faster than the Earth? I would like to give all of you, I'm going to give you a full minute to try to work this out. I think this is a very difficult problem. You're going to need maybe a little piece of paper to think about it. And the hint I want to offer you is you're going to need Kepler's third law to translate the distance of the asteroid from the sun to the time it takes the asteroid to go around the sun, the orbital period. So I'll give you a full minute. You're welcome to talk with anybody you want to or work by yourself. In a minute, I'll ask for your colored pieces of paper. Do you have an answer? Well, go ahead and show me your colored pieces of paper. I'll tell you what colors I see. If you don't put up a colored piece of paper, then I will ask you personally to describe how you got your answer. We need more colored pieces of paper. I see one here. Who still needs colored pieces of paper, by the way? Go ahead and raise your hand. Okay, let me tell you the colors I see. Greens, reds, blues, and a yellow or 2 or 3. Greens and reds are about equally numbered. But I don't even know the answer myself. I see a laptop with the letter D, no, a pad. Well, I want to do the problem 2 different ways. First, let me give you my off-the-cuff logic answer, and then I'll give you an answer that we approach with some equations. Here's the logic. Please follow me. This asteroid is farther from the sun, so it has farther to go in its circumference around its orbital circle. So at first glance, I would say to myself, well, gee, this asteroid has much farther to go than the Earth does in its 1 AU radius circle. So that's a burden for the asteroid. The question, of course, is, how long does it take the asteroid to go around that circumference? I don't know the answer off the top of my head, but I would say that Kepler's third law, which says that the square of the orbital period is equal to the cube of the orbital radius, the semi-major axis, p squared equals a cubed, that tells me that this asteroid being farther from the sun is going to take longer to go around the sun. So I don't know whether it's going faster or slower, but it's going to take a longer amount of time. Now, in a way, that kind of balances the large circumference. This asteroid has a long way to go, and we know from Kepler's third law already that this large distance plugged into p squared equals a cubed means it's going to take a longer amount of time. So how do those 2 things balance out? The larger distance it has to go and the longer amount of time, the longer orbital period. We're going to need to handle both of those because velocity is distance traveled divided by the amount of time. So I talked this through so you could sort of feel the logic that's sort of bouncing around maybe in your heads as well as mine. You have to sort of sense what are the issues here, distance traveled and the amount of time to travel that distance. So let's calculate them. Here's how you do it. Let's start with the Earth. That's the easier case in point. How fast does the Earth go in its orbit? Well, here's the Earth. There's a velocity for the Earth, distance traveled over time. I know that the circumference of a circle is 2 pi times the radius of the circle. 2 pi times the radius. And the amount of time it takes the Earth to go around its orbit, 1 year. So that's the time in the denominator, 1 year. I'm going to leave my answer in that form. Of course, I could carry out the math on a calculator, but let's leave it this way. Why? Because when I now go and do the same calculation for the asteroid, I can also leave the 2 pi and maybe the units that are kind of weird, AUs and years and so on. So if I do both the Earth and the asteroid, calculate them both in the same way, I might be able to compare the two answers without actually punching numbers into a calculator. Very powerful. Okay, let's do the asteroid. Its orbit is larger. There it is. It's not drawn to scale, but it has an orbital radius of 4 AUs. So let's calculate the speed of the asteroid. Well, the speed of the asteroid, the velocity of the asteroid, is the distance traveled over time. It goes a circumference of 2 pi, and now the radius is 4 AUs, not 1 AU, so 2 pi times its radius. And how long does it take the asteroid to go around once? What's the orbital period? Well, we better use Kepler's third law. P squared equals a cubed. Plugging in, we have p squared is equal to a, which is 4 AUs, cubed. We actually did an example like this last week. 4 cubed is 64. And so p, the period, is the square root of 64. In other words, 8 years. So the asteroid takes 8 years to go around once, but its circumference is larger. Putting all the pieces of the puzzle together, we have that the speed of the asteroid is distance divided by time, 2 pi times the radius divided by the time, 8 years. I'm not going to work that out. I'm just going to compare that answer to the answer we got for the Earth. Let's compare that answer for the asteroid to that answer for the Earth. And by comparing the two, there and there, look at these two right-hand sides. We have a numerator with 1, but for the asteroid, 4 AUs, a factor of 4 bigger. But the asteroid has 8 years in the denominator, whereas the Earth has only 1 year. So the denominator for the asteroid is 8 times larger than that for the Earth. And so you can see immediately 4 divided by 8 is a half, and that's the difference between the asteroid speed and the Earth speed. In other words, the asteroid goes about half as fast. So that's the answer, B. The asteroid goes half as fast as the Earth. This is not an easy problem. We had to put a lot of pieces of the puzzle together. 2 pi r for the circumference of the circle. Speed is distance divided by time. And we needed Kepler's third law. And this is typical of a complicated problem in daily life. No matter what it is you're doing, you have to bring different pieces of the puzzle together and treat each one of them carefully. Okay. Now let's move on from position and speed and talk about acceleration. And I think all of you know a little bit about acceleration. By definition, it means the rate of change of velocity. How fast is the velocity itself changing? And the units of acceleration are speed that changes over a certain time, so it's speed, meters per second, per second, often written as meters per second squared. So acceleration is the change in velocity per second or per hour. And because velocity is a vector having a magnitude, an amount, and a direction, so does acceleration. So acceleration occurs if the speed changes, but also if the direction of motion changes. Going around a corner, you're accelerating. Changing speed by putting your foot on the gas pedal, you're accelerating. Putting your foot on the brake to slow the car down, you're also accelerating, but in the opposite direction. That would be called a negative acceleration. So acceleration occurs if you're changing speed or changing direction. And all of you know that when you drop an object, it accelerates due to gravity. So for example, if you have an object like this little box, if I drop it, it starts right now at 0 velocity, and it gains speed faster and faster. So it's accelerating due to gravity. We'll talk about that in a moment. And gravity works in a way that many of you are familiar with. An object that is falling falls at a constant acceleration, sometimes called little g. And little g, the acceleration of an object, the rate at which its velocity increases as it falls, is 9.8 meters per second per second. Don't let your eyes glaze over. What this means is something very intuitive. An object falling gains a speed, an additional speed of 9.8 meters per second every second. 9.8 meters per second per second. So as an example, when you drop something, after 1 second, its speed is 9.8 meters per second. Not meters per second squared, its speed is 9.8 meters per second. After 2 seconds, the speed has increased by another 9.8 meters per second, up to 19.6 meters per second. And finally now, here's a quiz question. After 3 seconds, what will the speed of the object be that's been dropped? Here are your 4 choices. I'll give you a moment to think about it. All right, show me your answer. How fast is it going after 3 seconds? I see A's and B's, a couple of D's even, but maybe that's because you're still flipping the paper. Here's the way I work this out. Objects fall at a constant acceleration. So if it went 9.8 meters per second after 1 second, 19.6 meters per second after the next second, 1 more second later, it will have gained yet another 9.8 meters per second. I can't add in my head, but 9.8 is approximately 10. So if I add 10 to 19.6, I get 29.6. And that looks about like answer A. So constant acceleration is something very common in our lives. An object whose speed is increasing at a constant rate, it's kind of funny to say it that way, is what we mean by speed increasing with a constant acceleration. Okay? Now, I would be remiss as a Berkeley professor, they might dock my pay, if I didn't remind you of something you all basically know, and that is that the motion of objects can be described by positions, speeds, and accelerations, and those 3 quantities are related by mathematics. And the best way to describe position, speed, and acceleration is with calculus. Many of you have had a little bit of calculus. You don't need to know calculus for what I'm going to tell you, but I want to give you a taste of calculus, the essence of calculus, everything you ever need to know if you haven't taken a course in calculus. Here it is. There's something called differentiation, and that's simply the following. Speed, velocity, is the change in position, x later minus x initial, the change in the position s or x over the course of some change in time. You start your stopwatch at t1, maybe that's 0, and you stop your stopwatch at t sub 2. That's some duration of time. The distance you went, the position after minus the position initially, divided by the amount of time, that's a delta, or a change in position, divided by a change, or a delta, in time. The Greek letter delta is used always to mean a change in something. So we write it as velocity is the change in position over the change in time, the amount of time that went by. And that's calculus. Velocity is sometimes said to be ds dt, d being short for this delta. Delta s over delta t. Similarly, acceleration is the change in velocity over the course of some amount of time, delta velocity divided by delta time. That's calculus. You can always specify the acceleration of any object in the universe by the change in its velocity over the change in time, by how much time went by during which it changed its velocity. And to be a little more honest, in calculus, as many of you know, it's best to shrink delta t down to a really tiny interval of time, a second, a thousandth of a second, a millionth of a second, and then the speed is the instantaneous speed or acceleration. Okay, so that's differentiation. What's the take-home point? That there's an intimate relationship between the position, the speed, and the acceleration of an object. You can write down each of the three of them, and they're related to each other by how much one changes over the course of time. Similarly, you can let certain quantities accumulate over time. And when you talk about the accumulation of something, like the position of an object that's moving with a speed, it goes a certain distance after a certain time, and then after a little more time it goes farther and farther and farther. That accumulation of distance is called integration. So if you want to know the position of something, there's something called integration, which I won't talk about. It's basically a sum, which is why this looks like a capital S. Integration is just summing velocities over the course of time. And similarly, without further ado, velocity can be written as the sum of accelerations over the course of time. And my only point here, this won't be on the midterm, of course, but my point is to give you a flavor for the idea that with a little bit of calculus, you can interrelate position, velocity, and acceleration with simple ideas of calculus. Now, let's talk for one moment about a falling object, like a falling ball, a baseball that's in the air and it's falling, or a football. In the case of an object falling, it is accelerating due to gravity. And we say that the gravitational acceleration is little g, 9.8 meters per second, but we put a minus sign in front of it to specify that objects falling are not accelerating upward, they're accelerating in the downward direction, so we use a negative sign. So we would say the acceleration of a falling object is minus 9.8 meters per second. And then, again, without further ado, let me just say that velocity and position, like the height of a ball that's being dropped, the height is a function of the initial height and the acceleration and how much time goes by. And this is a very well-known equation for constant acceleration and similarly for velocity. And my only point, and none of this will be on any test you'll see, but the point is you can relate positions, velocities, and accelerations, especially in the case of constant acceleration, with very simple equations that stem from, the first few weeks of a calculus class. Okay? That's all the calculus you need to know for the rest of your life. Now, I want to talk a little more about acceleration, and I brought a 2-minute video on how acceleration plays a role in normal life, for example, an automobile. So here's a little 2-minute video on accelerations for fast cars, I think. Went into the trunk of the car. How did they? That's the craziest darn thing. I've never seen anything like that. Did you see how that worked? The trunk opened up in the back and the top went in? How that happened. So let's calculate the acceleration. We have a way of doing it ourselves. There's the change in velocity. It went from 0 to 60 miles per hour, which in meters per second is 0 to 26.8 meters per second. And it changed its velocity that much in 4.9 seconds. So the acceleration, by the definition that we were just talking about a moment ago, is the change in velocity, the delta in velocity, over the course of a certain amount of time. And so you can calculate the acceleration of the Ferrari by the change in velocity, 26.8 meters per second, in 4.9 seconds. Doing the division with your calculator, you get 5.47 meters per second squared. That's the acceleration. That's the same as saying 0 to 60 in 4.9 seconds. Okay? So that's all there is to acceleration in the linear sense, but keep in mind that acceleration also includes changing direction, like taking a corner. Now I want to talk about the other major type of physics that Isaac Newton illuminated, and that, of course, is gravity. So I'm going to talk for the next 10 minutes about the nature of gravity, which, by the way, is the one force that governs the entire universe. All of the motions of planets around stars, stars around galaxies, galaxies around other galaxies, and galaxy clusters moving relative to the others is describable simply by taking into account the force of gravity. It's the one by far dominant force in the cosmos. So, to remind you, there's a law of gravity. We talked about it briefly before. It pertains not just here on Earth to an apple falling off a tree, but also to the moon dropping toward the Earth, or the Earth dropping toward the sun. And the law of gravity is that every mass is attracted to every other mass. The amount of attractive force is proportional to both masses. Both masses enter into that equation for force symmetrically. I say symmetrically because the algebra has a symmetry. Both masses are treated equally in their gravitational attraction for each other. And then finally, the gravitational attractive force is inversely proportional to the distance squared, d squared. And so all of you have seen this equation. The force of gravity is equal to the product of the masses divided by the distance squared. And then there's a proportionality constant called the universal gravitational constant, capital G. And nobody knows why it is that the universe, our particular universe, has the value of G, capital G, that it has. So with that, I'd like to talk a little more about gravity, but let me just point out one subtlety, but it's profound. Notice the left-hand side. F sub 1 is the force acting on mass 1, pulling it toward mass 2. F sub 2 is the force on mass 2 pulling it toward mass number 1. Those two forces are equal and opposite. And so I've written them both here. Whenever one object is exerting a force on another one, that other object is exerting the same exact force on the first one. And so it is with gravity. So there are really two forces in this problem, the force on mass 1 and the force on mass 2, and they are absolutely equal given by this equation. Now here's a quiz question, so get your colored pieces of paper out. Suppose you had long arms and you could grab the moon, and by grabbing the moon you pull it in to the Earth. Suppose you pull the moon in to 1/3 of its current distance, so that the moon is only 30% as far away as it actually is. The moon would be much larger, it would loom 3 times larger in the sky. The distance is 1/3 of what it was. And the question you know I'm going to ask is, what is the gravitational force exerted by the moon pulling, yanking gravitationally on the Earth? What is the gravitational force that the moon exerts on the Earth? Is it 9 times greater than before, 3 times greater than before, 1/3 as great as before, in other words, weaker, or 1/9 as great as before? Give yourself a few seconds to think about this. Is the force bigger or smaller, and by how much? All right, show me your colors. Got an answer? This is a tough one. So I see blues and reds and greens, for what it's worth. I don't know how to do this problem either. Let me talk through what I would do. If the moon is closer, 1/3 as far away, I have an intuitive feeling that this moon that's closer is going to pull more strongly because it's close. Like two magnets close to each other pull more strongly. The moon closer to the Earth is going to pull more strongly. And I know that the distance comes in squared, why did I say cubed? Squared in the equation. So if the distance is 1/3 as much, and it comes in squared, 1/3 squared, 1 divided by 3 squared is 1/9. And so I think in the denominator I have a distance now, but squared, that's 1/9 of what it was. The denominator is 1/9 as big. It's smaller by a factor of 9. And so the whole equation for the force is 9 times larger. And the right answer then really is A, 9 times greater. Is that right, or did I make a mistake? So if the moon is 3 times closer, the force is 9 times greater. And of course the Earth is yanking on the moon 9 times more strongly than the Earth was yanking on the moon before. Okay? Now, one of the strange aspects about gravitational acceleration, 9.8 meters per second, is that it doesn't matter how massive the object is. If you drop a bowling ball, it accelerates down at 9.8 meters per second per second. If you drop a feather and let it drop, it will also accelerate downward at 9.8 meters per second per second. Gravitational acceleration downward doesn't care what the mass is. Well, except that here on the Earth we have air, and the air offers air resistance. So the feather, as it's accelerating downward, will run into air molecules that will pummel the poor feather, slowing the feather down as the molecules hit the underside, the lower side of the feather. So if you want to verify that a bowling ball and a feather drop at the same acceleration, look how happy he is. Hopping around. So it's pretty cool. It is true that objects fall at the same rate. The famous example of Galileo, you may have heard the story, went to the Leaning Tower of Pisa in Italy, which kind of is at an angle, and he dropped rocks of different masses off the top of the Leaning Tower of Pisa, and they hit the ground at the same time, independent of their mass. There's another aspect of gravity that's interesting. Everything is falling toward the Earth, including the moon. And if the moon is falling toward the Earth, why doesn't the moon crash into the Earth? And the answer, of course, is that the moon is not only falling directly toward the Earth, but in addition, the moon has some velocity already, sideways. And those two have to be taken into account together. And I hope I can do this. There we go. So here's a cannon right there. And with this demo, I'm going to shoot a cannonball at a certain speed. Gravity, of course, will pull the cannon toward the Earth. So let's go ahead and shoot the cannonball with a speed shown up here, 1 kilometer per second. That's a pretty fast speed, by the way, for a cannonball. So I'm going to shoot with this little dangerous green button here. Here we go. Watch the cannonball falling by gravity with a certain side velocity, horizontal velocity of 1 kilometer per second. Here we go. All right, let's reload and try it again. Here we go. Gravity is causing the cannonball to drop at 9.8 meters per second each second, 9.8 meters per second squared. Let's increase the speed of the cannonball maybe up to what, 3 kilometers a second. See, the young boys in the room here wanted to go to 5 kilometers a second, and we'll just go a little more slowly. Reload. Ready? 3 kilometers a second. Cool. All right, let's do it again. Fire. It's still falling at 9.8 meters per second squared, but it travels farther in the horizontal direction while it's dropping, and it hits the ground after the same amount of time, because the vertical acceleration downward is unaffected by the horizontal. Now let's go up. Okay, let's go to 5 kilometers a second, like you said. There's 5. Reload. You ready? Here we go. 5. That's cool. Should we go up more? 6. Here we go. Ooh. All right, 7. I'll buy it. I'll go a little more. 7 kilometers a second. Ready? Go. Oh, heartbreak. All right, I'm ready to try 8. 8 kilometers per second. Ready? Let's go Bears. Soccer team. Down in front, soccer team. Okay, we'll try it again. Reload. That was the soccer team. Go again. 8 kilometers a second. The cannonball is still dropping at the same acceleration, little g, 9.8 meters per second squared, that it was before. But while it's dropping toward the Earth, it's also going horizontally. And so while it drops, it simply continues around, curving around, falling every second of the way. The moon, in its orbit around the Earth, is falling the whole time. The space shuttle, the space station, all of the satellites orbiting the Earth are falling toward the Earth at 9.8 meters per second squared. But as they fall, they're moving horizontally, and that carries them around the curvature. By the way, let's try a faster velocity, A. How about 10? Okay? Here we go. 10 kilometers a second. What will happen? It's got a velocity so fast that it actually goes beyond a circular orbit. And did it leave the Earth? Cool. Notice one of the aspects of gravity. It causes the orbit to be closed, a closed shape. Obviously, and you all know this, it is the shape of an ellipse that Kepler figured out many years prior. How about a little faster velocity, by the way, just for fun? All right, 15. Reload. Ready? Go. Oops. I don't think that's coming back. There's a velocity called the escape velocity from every planet. The escape velocity is the speed that's so great that when you shoot something, whether it's a rocket, a cannonball, or a baseball, if you have a good arm, the object will actually leave the Earth never to return, escaping the gravitational grip of the planet. Okay? So the moon is subject to gravity. The moon is falling toward the Earth, but it's falling while it moves sideways. I think that's pretty cool. And here's another short video on the nature of gravity. Einstein actually developed a new theory of gravity that's just a little bit more precise, and it works in the cases, the rare cases of extreme gravity, extremely strong gravitational forces. You need to use Einstein's general theory of relativity. But meanwhile, for almost all of our applications, Newton's laws of physics are totally adequate. And he developed 3 laws of motion, and I'd like to finish today's lecture by describing those 3 laws of motion, many of which are sort of obvious to you, but maybe not. And so you might want to watch carefully and think about this. Newton's first law of motion says an object moves with a constant velocity unless acted upon by a force, in which case the object changes its velocity. And so a spacecraft moves in a straight line in space unless there's some gravitational force acting on it. On a billiard table, the balls stay stationary if there's no force on it. If the ball's moving with a constant velocity and there's no other forces acting on it, the ball remains moving at a constant velocity. And only if you apply a force does the ball change its trajectory. So that's a case where an object in motion remains in motion at the same speed unless a force acts on it. The most important of Newton's laws is the second law. It says that an object will accelerate when it experiences a force, when a force is exerted on it. And the second law says that the amount of acceleration is directly proportional to the force exerted on it. Here it is, that second law of motion. The acceleration of an object happens because a force was exerted on it, and the acceleration is proportional to that amount of pushing or pulling, the force on the object. And by the way, the units of force are the Newton. The Newton is the unit of force in metric units. So the units of force are Newton. The units of mass, as I've already mentioned, is kilograms, you all know. And the units of acceleration are meters per second squared, which I've written as meters second to the -2, a different way of writing it. How do you make a baseball go from rest, stationary, to 90 miles an hour when it crosses home plate? Well, the pitcher has to apply a force during a very small amount of time. By applying that force, making the ball accelerate up to its final speed. And so there's Bumgarner applying a force. You can see how much force he's applying to the ball, and he only has a half a second or so to apply that force and make it go to the speed that it finally goes. If you're kicking a soccer ball, you only have a fraction of a second to impact the soccer ball, apply a force, and accelerate that ball up from its initial velocity of 0 to its final velocity. Same with a baseball bat hitting a baseball. There's a fraction of a second when that baseball bat applies a force and causes an acceleration to the ball. This proportionality constant is the mass. It's a funny quantity. I won't talk much about it, but the amount of kilograms that something has, the bulk mass of something, is a kind of a resistance to acceleration. More mass for a given force means smaller acceleration, because mass times acceleration is the force. Other examples that we've already discussed, a race car. How does a race car go from 0 to 60 miles an hour in 4.9 seconds? Somebody somewhere is applying a force. And if you think about it for a moment, it clearly is the automobile engine that's applying the force. But what is it applying a force against? What's pushing on what when a car goes forward? Clearly the answer is that the rubber of the tires is pushing very hard against the planet Earth. And so it's the tires of a car that are applying a force, pushing the Earth backward, and there's an equal and opposite force on the race car so that it accelerates forward as the Earth accelerates backward. Of course, the Earth accelerates backward a very tiny amount. Why? Because the mass of the Earth is so large that for a given force, the large mass of the Earth means a very small acceleration will give you that same force. Here's a little quiz. You only need your red and your green colors. There's only a yes or a no, so red or green are your only two options. Question 1, when a car comes to a stop, is there a net force on the car? You can show me your colors right away. Yeah, the answer is yes. When a car comes to a stop, there's a force on that car. The brakes are applying a force that causes the car to accelerate, okay, in the negative direction because you're coming to a stop, but still an acceleration in the negative direction is a force in the negative direction. That's what your brakes do. Is there a net force on a bus that's speeding up? I think all of you know the answer is yes. I see everybody with a red A. What about an elevator moving at a constant speed? Is there a force on an elevator when the elevator's going up or down at a constant speed? This one's not so obvious. I see different colors. Strictly speaking, an elevator moving at constant speed has no net force on it. Net force. Why do I add the word net? Because clearly gravity is pulling the elevator downward, but there's some kind of a machine, a pulley system, some motor that's pulling the elevator upward against the force of gravity downward. Those two forces must oppose each other so that there's no net force, how do we know? The elevator is moving at constant speed. It would be accelerating if there was a net force on it. How about a bicycle going around a curve? Is there a force on a bicycle going around a curve? Yeah, the answer is yes, as I think all of you can see, because somehow the bicycle has to be pushing against the Earth, otherwise it would slide off into the curve. And finally, what about a moon of Jupiter, orbiting Jupiter? Is there a net force on a moon of Jupiter? I have to tell you, this is a trick question, so don't worry whether you put A or B. Strictly speaking, I would say yes, there's a force on a moon orbiting Jupiter. It's the gravity of Jupiter pulling on that moon. Otherwise, the moon would go flying off. It's a little bit of a subtle point. And then finally, I've mentioned this, Newton's third law says that for every force, there's an equal and opposite other force. So for example, there's our friend Isaac watching an apple fall from a tree. It's obvious that the apple is falling because it is experiencing a force of gravity on it, pulling the apple downward, but there's an equal and opposite force on the Earth, pulling the Earth upward toward the apple. The Earth is accelerating upward, and the apple is accelerating downward. Now, you might say, wait a minute, okay, I understand that. Rockets are another good example. We'll come back to the apple in a second. In a rocket, the rocket experiences a force that makes it go up because the gases out the back end are being forced backward. So as long as there's a force that pushes the gases downward, there has to be another force, equal and opposite, on the rocket in the other direction. You might want to think about that. Fine, but what about the apple? The apple is pulled downward. You can see an apple drop. Why doesn't the Earth accelerate upward to meet the apple? And the answer is that the Earth is so massive that in force equals mass times acceleration, yeah, the Earth is experiencing a force, but the Earth's mass is so large that its acceleration is tiny. So that's the difference. And then finally, one last note. The law of gravity explains how the Earth goes around the sun, and indeed how all the other planets go around the sun. It's gravity that holds the planets to the sun. And by the way, the planets are yanking gravitationally on the sun, right? And it's the law of gravity, just like the motion of the moon around the Earth, that causes the planet to go slower when it's far from the sun, pulls it in faster, so that all three of Kepler's laws that we discussed last week, all three of Kepler's laws follow directly from the law of gravity, and force equals mass times acceleration. That's second law. And so I'll just say that more clearly, that this Kepler's law, p squared equals a cubed, that we discussed last week, is something that Kepler noticed by looking at Tycho Brahe's observations of the planets, notably Mars. But it turns out Kepler's third law follows directly from Newton's law of gravity with a little bit of algebra. You can write the algebra on the back of an envelope and derive, just with a little bit of algebra, Kepler's third law. Here's what Newton derived. P squared is equal to a cubed, but guess what? There's a proportionality constant. Here it is, 4 pi squared over capital G, with the sum of the masses, the star or the sun and the planet being the two masses that go down there. So Kepler didn't know there was a proportionality constant. He used units that made it go away. But Newton showed that yes, Kepler's third law is right, p squared equals a cubed, and the proportionality constant includes the masses of the two objects, m1 and m2, that are orbiting each other. So with that, I will quit for today. Next lecture is very important on energy.